All right, so to introduce stoichiometry is essentially just using a chemical equation like our recipe. So you can figure out how much product you're going to get from a certain amount of reactant or how much reactant you need to make a certain amount of product. So if you're making cookies and you only have one egg and you want to follow the recipe exactly, the recipe calls for 2 eggs and the recipe produces 5 dozen or 60 cookies. So if you only have half as much of an ingredient, then you can only make half as many cookies, right? So you're going to make 30 cookies if you only have one egg, assuming you have plenty of everything else. Well, a chemical reaction, a chemical equation is really no different, except that we're talking about molecules instead of cups and tablespoons. So we can think of the reaction above as a recipe that calls for 2 H2 molecules. Oops, there we go. And 1 oxygen molecule. And results in 2 water molecules. Okay. And so that's what those coefficients stand for. They stand for molecules. But because molecules are so small, we probably would do better to think of them instead of molecules. We would probably be better to think of them as moles, right? So, in other words, 2 moles of hydrogen combines with 1 mole of oxygen to produce 2 moles of water. It's probably a better way to think of it. So you can say these molar ratios from this balanced equation in a lot of different ways. You could say that there's a molar ratio of the 2 ingredients. You could say 2 moles of H2 for every 1 mole of O2. You could say it as a fraction. 2 moles of H2 over 1 mole of O2, right? And you could write a bunch of them. You could say for every 1 mole of oxygen we use, we get 2 moles of water. Or we could flip it, right? We could say 2 moles of water are produced for every 1 mole of oxygen used, right? There's a whole lot of different ways to say essentially the same thing. And that is essentially just saying that the coefficients stand for moles, right? So a very simple stoichiometry problem we could do. It says in order to produce 3 moles of water, how many moles of oxygen would we need? Well, we already have this ratio, right? This ratio tells us that we only need 1 mole of oxygen to produce 2 moles of water. Of course, along with 2 moles of hydrogen as well. But this is just asking us how many moles of oxygen would we need, right? And since we have that 1:2 ratio of moles of oxygen to moles of water, if we wanted to produce 3 moles of water, we would need, right, about half as much, 1.5 moles of oxygen, okay, because of that 1:2 ratio. 3 to 1.5 is, of course, the same thing as 1 to 2. Or I should say the other way around. 3 to 1.5 is the same thing as 2 to 1. Okay. It says, according to the reaction below, how many moles of dinitrogen pentoxide would be produced if you use 7 moles of oxygen with excess nitrogen? So the excess nitrogen part just means don't worry about the nitrogen. We have plenty of it. But let's just base this on using 7.0 moles of oxygen. And we are simply going to convert this using just a little conversion factor from moles of oxygen to moles of N2O5. And hopefully you can guess what that ratio would be. We just look at the balanced equation, right? So next to moles of N2O5, we've got that 2. And so that's going to be our number of moles of N2O5. And then next to moles of oxygen, we have that 5. And so that's the number that's going to go on the bottom there next to moles of oxygen. And so that cancels moles of oxygen. It leaves us with moles of N2O5. And so 7 times 2 divided by 5. And that should give us about 2.8 moles of N2O5. Okay, There we go. And that's stoichiometry. Basically, that's an example of a very simple stoichiometry problem. All right, the next question says how many grams of oxygen would be required to produce 0.5 moles of N2O5. So we're starting with 0.500 moles of N2O5, and that's going to go over 1. We're just doing a conversion. And we know we want to get rid of moles of N2O5, so that's definitely going to go on the bottom. The difference is this time it's not going to be a one-step problem because it's asking me for grams of oxygen, right? And there's a 5 in front of oxygen, but that's not grams, right? That's moles, all right? So whenever we have grams in a conversion for an element or a compound, then we're going to go to the periodic table for that. But we can't do it in just one step. We're going to have to go from moles of N2O5 using the balanced equation. We're going to this time go to moles of oxygen. So essentially the opposite of what we just did. So those numbers are going to come from the coefficients. Only this time it's going to be 5 on top and 2 on bottom, right? So that takes care of moles of N2O5. And now we have to take this to from moles of O2 to what it's asking us for, which is grams of O2. And we know how to do this already, right? Anytime you have moles and grams of the same substance, we just say 1 mole equals, and then we go to the periodic table, right? And so oxygen has a molar mass of 16, but there's 2 of them, so that would be 32, okay? So 32.00 grams of oxygen. And so now it's just going to be a matter of plugging it in the calculator, and we should get about 40.0 grams of oxygen. And there we go. All right, this next problem is asking us for moles of acetone needed to burn to produce 225 grams of CO2. We do need a balanced equation for this one, so see if you can come up with that. Go ahead and pause. Okay, so there's our balanced equation. And now we're going to start this time with grams of CO2. So 225 grams of CO2. And we are going to take that to moles of acetone. Without even really thinking, we know we need to get rid of grams of CO2. And as much as I would like to put moles of acetone on top, there's no relationship between grams of one substance and moles of a different substance. But I can go to moles of that same substance. That is something we should be very familiar with at this point. That's just using the periodic table, right? So 44.01 grams are in 1 mole of CO2. And now I have moles of CO2. And since I have a balanced equation, I should be able to take that to moles of acetone. And so that, from my balanced equation, is just 1 to 3. All right, and again, since we're at the answer that we want, now it's just a matter of plugging it in the calculator. And I got 1.70 moles of acetone. Here we go. Okay. All right. One more problem here. How many grams of fluorine gas would be needed to fully react with 10.9 grams of gallium chloride? So once again, see if you can predict products and balance for this reaction. Okay, so hopefully you came up with something like this, a single replacement reaction. All right, and our starting point, of course, is going to be our 10.9 grams of gallium chloride. So 10.9 grams of GaCl3. And we have to take that all the way to grams, to grams of fluorine gas. So this one is a unique problem. We haven't done one quite like this yet. We're going all the way from grams of one thing to grams of something else, right? But you will know all the steps. It's just a matter of putting them together. the first thing we would do, much like the previous problem, is we're gonna go from grams of whatever we were given. In the previous problem, it was 225 grams of CO2, right? This time it's 10.9 grams of gallium chloride. And then we're going to go to moles, right, using the periodic table. And the periodic table says that gallium chloride is 170.07 grams per mole, right? So now I have moles of gallium chloride. And again, I'm trying to get to grams of F2. But I can't go there from moles of a different substance. But hopefully at this point you kind of have the idea that I could go to moles of F2 because I have a balanced equation. Anytime we're trying to go from moles to moles of two different substances, we have to use the coefficients from the balanced equation. So those would be 3 and 2, right? And then from moles of fluorine, it becomes, again, a very familiar process. Using the periodic table, looking up fluorine and multiplying it by 2 should be about 38 grams per mole. And this comes out to about 3.53 grams of F2. And if I just kind of use just a very rough mental check, 10.9 grams to 3.53 grams, those aren't such different numbers that it seems crazy to us. So that seems like it makes sense. Last little thing here, this little box here is just saying to us that we can basically always go from grams of substance A to grams of substance B, but we can see that it's going to take multiple steps, right? Because the first step, as we just did, was to go from grams of substance A to moles of that same substance. And then once we get there, we can use the balanced equation to then go to moles of substance B, a different substance, in the balanced equation. And then we could use the periodic table to go to grams of that same substance. So hopefully that little diagram will, either you'll look back at it or you'll remember it, because it kind of gives you an idea how many steps are going to be in the process.